Hello everyone, my name is Amza Shami bin Abdurrahim, and today I'll be explaining about preemptive priority, which is from chapter 5 CPU scheduling. As you can see, there's a table here with 5 processes, process 1, 2, 3, 4 and 5. Each of them have their own arrival time, burst time and priority. Arrival time is the time the process arrives, burst time is the total amount of time it takes for the process to run, and priority is the order of which process is executed first. The lower the number, the higher the priority. So you can see here P4 has the lowest number at 1, and so it has the highest priority among all the other processes. And now we'll begin constructing the Gantt chart. Before we construct the Gantt chart, we first calculate all the burst time and add them up together. So we'll add up 7 plus 4 plus 3 plus 2 plus 5, and it will add up to 21, which I'll put here as a note. To construct the Gantt chart, we must first find which process arrives first, because the Gantt chart always starts at 0 millisecond. And if we check here, process 1 arrives first at 0 millisecond, so process 1 will be executed first. After we figure out which process has arrived first, we will do something called the ready queue, where we will put on all the available processes that has arrived under the table for our reference. So right now we only have one process, which is P1, and we'll put together its burst time plus its priority, which is at 5. With that done, we can now proceed to the next process. To figure out the next process, we must check which the next process arrives at what time. As you can see here, P2 is the next process and it arrives at 1 millisecond. So because of that, P1 has to be interrupted so that we can check whether P2 can be executed or not. Because in preemptive, an interrupt will occur if a new process arrives or once the current process terminates. Over here, we'll put 1, signaling the time P1 stops and P2 arrives. And before we decide what to put inside this box, we must first prepare a ready queue. Right now we have P1 in our ready queue, and it will only be equal to 6 milliseconds of burst time because it has already run from 0 to 1. So you have to minus 1 and it will have 6 milliseconds of burst time, and the priority remains the same at 5. But we also have P2 which has arrived, so let's also add P2 to our ready queue. And P2 has a burst time of 4. So we will put that too. And has a priority of 4. And now we have to decide which of this in the ready queue has the highest priority. Because in preemptive priority, the higher the priority, the higher the order of which the process will be executed. And you can see here, P2 has the higher priority compared to P1 at 4. So we will now execute P2, and I'll highlight P2 to make sure that we know that it's in. Okay, and now we'll include P2 into the Gantt chart. And once you have included P2, we can now focus on the rest of the Gantt chart. And the next time where the process will stop is at 3 milliseconds because process 3 arrives. So we'll stop at 3 milliseconds. And now we'll update our ready queue. P1 will be the same as it hasn't run. We then have P2 over here, and P2 has run for 2 seconds from millisecond 1 to millisecond 3, so we have to update the burst time. So now P2 will have a burst time of only 2 and the priority remains the same. And now we have to include P3, which has arrived into our ready queue. P3 has a burst time of 3 milliseconds and he has the priority of 2. And now we have to figure out which has the highest priority for us to put inside the box. And we can see that P3 has the highest priority at 2 compared to P2 and P1. So we will now execute process 3. And once you have done that, we can now continue to the rest. The next interrupt will occur at millisecond 4 because process 4 arrives. And as usual, we will now be upgrading our ready queue. And P3 will be updated because it has run for 1 second. P3, the burst time will be updated to 2 because it has run from 1 second from 3 to 4 milliseconds. The priority remains the same. We will now include P4 into our ready queue because P4 has arrived. P4 has a burst time of 2 milliseconds and a priority of 1. You can see since it has the priority number of 1, it has the highest priority among these processes and will be executed first. This highlighting is to ensure we know which process is executed at each box. And after that, the next interrupt will occur at 6 milliseconds because process 5 arrives. And we will update our ready queue as usual. Now we will decide which process will be executed based on the priority. And P3 has the lowest priority at 2 and it will be executed this time. And then we've done that. We will now let P3 run till the end because we don't have any other process that arrives after 6 milliseconds. And the current processes and the upcoming processes are free to run until they are finished executing. And we'll let P3 run to the end and finish off its 2 millisecond burst time. And it will end at 8 milliseconds. And we will continue our Gantt chart down here because there are still a few processes left. The Gantt chart over here will begin at 8 milliseconds. P5 has the lowest priority as the highest priority at 3. And will be executed. And it will be run until it ends its burst time, which will end at 8 plus 5, which will be 13. And after that, we can begin our execution for the next process based on our current ready queue. Only left P2 and P1. And now P2 will be executed because it has a higher priority than P1. And P2 will be executed for 2 seconds, which is the balance it has after running from 1 millisecond to 3 milliseconds. And it will end at 15 milliseconds. And finally, we only have one process left in our ready queue, which will be P1. We'll include that here. And we'll let P1 run till the end of its burst time. which will end at 15 plus 6, which is 21. The Gantt chart ends at 21 millisecond, which is same as the calculated total burst time for all processes, which is also 21 milliseconds. This is a way to ensure that your Gantt chart is done properly. And to calculate the waiting time, for P1 example, there's two different processes running at that run at two different times. So the formula to calculate that is, first we must determine the arrival time here in the Gantt chart, the response time, and we'll have to minus it by the arrival time in the table here, which is 0. And then we add it together with the second time it ran. We have to look at the response time at the time, which is 15 milliseconds. And we have to minus it with when it ended in the first time it ran, which is 1. And when we add them up, we'll get 14 milliseconds of waiting time for process 1. For process 2, it's a similar process as it ran twice. We'll first find the response time, which is first response time, which is 1, and we'll minus it by the arrival time in the table, which is 1. We'll add it up with the second response times, which is 13, minus it with the time it ended and the first time it ran, which is 3. And you have 10 milliseconds. For process 3, it also ran twice, so you follow a similar process. Find the response times for the first time it ran, minus it with the arrival time, which is 3. Add it up with the response time of the second time it ran, which is 6. Minus it with 4, which is the time the first process ended. And you'll be left with 2 milliseconds. For P4, it's straightforward because it only ran once from 4 milliseconds to 6 milliseconds. And how to calculate for this is you have to take the response time, which is 4 milliseconds, minus it with the arrival time, which is 4 milliseconds also, and you'll get 0 milliseconds. P5 follow a similar process to P4 because it ran only once, so we only have to calculate it once, which is the response time starting at 8 minus the arrival time, which is 6, and you'll get 2 milliseconds of waiting time. And we'll continue with average waiting time. To calculate average waiting time, we have to add up all the waiting time for all processes, which is 14 plus 10 plus 2 plus 0 plus 2, and we have to divide it by 5, why 5? Because there's 5 processes and you have to divide it by the total number of processes. And once you've done that, we will calculate and we'll have a result of 28 milliseconds, which will divide by 5, and the final result will be 5.6 milliseconds of average waiting time. And that will be the end of my explanation for preemptive priority from chapter 5.
Thank you, Hamza. Now I'm going to talk about the non-preemptive SGF shortest job first. Now, the table is the table at what me and Hamza use for our question. Now I'm going to explain what is non-preemptive SGF shortest job first. First, we need the Gantt chart. At time 0, only P1 has arrived as we can see here. So After basically P1 is the first non-preemptive. After that is 7, which this at the time 7 all other processes have arrived. So which is over here the burst time. So what we can do now is first we need the gunshot. At time 0 only P1 has arrived. So we run P1 as the first non-preemptive. P1 runs from 0 to 7. At time 7 all other processes has arrived. So P2 at 1, P3 at 3, P4 at 4 and P5 at 6. We choose the one with the smallest burst, which is P2, P4 with 2, P3 with 3, P2 with 4 and P5 with 5. So we plus the burst times with the numbers there. So 7 plus 2 we get 9 over here. 9 plus 3 you get 12, which is from the first time over here. Now 12 plus 4 you get 16, and then 16 plus 5 we get 21. Now for the waiting time, we have seen the formula here. TAT is okay. Waiting time. Okay, waiting time. As we can see here, the turnaround time is minusing with the burst time, or equivalently start time minus with the arrival time. Now for the waiting time, for P1 is 0, P4 is 3, P3 is 6, P2 is 11 and P5 is 10. As for the average waiting time is 30 divided by 5 because 6.00 ms. For average turnaround time is 51 divided by 5, which is 10.20 ms. That's all from me. Thank you.
Good day, everyone. My name is Ishwarnathan. Today, I'm going to present that topic 2, Banker's algorithm and safety algorithm. In this system, we have 5 processes P0 to P4 and 3 resources types R1, R2, and R3. The tables show the current allocation and maximum matrices. The total resources are R1 equal to 9, R2 equal to 6, and then R3 equal to 8. At first, we have to calculate need. Need formula is max minus allocation. Then here you can see the table of need. So it will become like this if we calculate. Then we have to calculate total instances. So for formula for get total instances is available minus sum of allocation. Here we can see total instances of resources. So for resources 1, 2, resources 2 is 4, resources 3 is 3. Now we have to calculate the safety algorithm. For process 0, it show true. So we have to update the available. So for next, we have to replace it the updated available here. So it's showing that true. Then we have to update the available again. Same to P2 and P3 and P4. We have to do the safety algorithm like before we did for P0 and P1. That means process 0 and process 1. All is true. So we have to do safe sequence. So first P0 and then following P1, P2, P3, P4. In the conclusion, the system is in safe state and this can finish without causing deadlock. Now we jump into next question. If process 1 requests 101, apply the banker's algorithm to decide if the request can be granted. Here is the way to check it's true or not by using request lower than or equal need. Now we check the safety algorithm after grant process 1 request 101. Here you can see the available after grant P1's request, allocation, and need to. For the other allocation and need still same because only process 1 changes. So now we have to run safety algorithm again. Here we can see that process 0 is no. So that means we have to do for next P1. So for P1, it's so yes. So we need to plus the available. So following that, we have to do for P0 because just now for P0, it shows no. So we have to make sure it yes. Then only we can make sure the safety algorithm is good. So for second time, P0 is yes, and then following yes. So the sequence is P1 is the first, and then following are P0, P2, P3, P4. In the conclusion, the pretended state in safe request 101 P1 can be granted. That means process 1 can be granted. Before I end, why must we check safety again after a request? Because even if the request is possible now, it might make the system unsafe in the future. Banker's algorithm ensures every request keeps the system in safe state. That's all. Thank you.